Thank you very much for coming. I'm Elvis, and as been mentioned, mostly known for various hacks in the async ecosystem of Python, UV loop async PG, EdgeDB tools, and, well, async await itself. But nowadays, I'm mostly working on EdgeDB full-time. If you've not heard about it before, EdgeDB is a relational database which acts as a PostgreSQL front-end replacement. It essentially sits in front of Postgres and adds new schema definition and a new query language, which we call EdgeQL. And then all of it is written in approximately 200,000 lines of Python plus an odd 30K of Rust, Python, and C. But this talk is not really about EdgeDB, but rather about some of the very interesting hacks in Python that we sort of discovered or had to invent a little bit to solve some challenges while developing EdgeDB. So the first thing I'd like to talk about is writing network clients. So if we have a database, naturally we want to talk to it from Python, right? And so that's what we set about to do. We are big fans of writing async first database clients, C async PG, and so that's what we did. And it's really simple. We basically interface looks like this. We send some message to the server by writing into our socket, and then we wait for that message to come back, and then we match responses, and so on and so on and so on. And that's how you would use it from Python. Now, of course, the world does not use async I/O exclusively. So, of course, we have to go back and write a synchronous driver as well. And that presents a little bit of a challenge since we have all of this code that we already wrote with async. And now, suddenly, you need to somehow either copy it or invent some sort of transformation to have a synchronous version of your network client or a database client. So what are the options? The obvious one is, well, just wrap it in async I/O run, wrap your methods in async I/O run, start the event loop, run that code, shut down the event loop, something like that. Well, it's cool, but unfortunately, it's very slow because you're essentially starting an event loop at every invocation. It will not work if there is already an event loop in your program running. It will complain that, hey, there's another event loop. I can't do this. And the most important part is that you cannot persist sockets this way because when you shut down your event loop, the sockets go away. So you would have to establish your connection every time you run that query and shut down the connection every time that query ends, which obviously is really, really slow. All right. So another approach is code generation, right? So we have this nice async code base. What can we do? All right. Well, we can do this. Like we can just strip away async def, replace it with def, strip away await, and boom, right? We have our synchronous client. Everything works. It's nice, except you no longer have a Python code base. Now you have some sort of template that you now need to run this generation script every time you modify it. You need to embed it in your CI. Your engineers need to know that you need to run this. It's a whole mess. Not to say that code modding like this can sometimes be very fragile. Yeah. So, right. Are there any other options? What can we do? Well, it turns out that what is a coroutine? A coroutine is essentially a generator. And prior to Python 3.5, there were actual generators, right? And so you can start that coroutine by calling a special method called send on it and passing it none. So that's how you can invoke a coroutine from Python directly. And the question is, OK, so we have a sync I/O event loop. Can we build a very, very simple rudimentary event loop for our async code base that would turn it into a sync code base, essentially. It turns out that we can. And this is the entirety of that event loop. Let's go line by line. So coro.send none essentially invokes our coroutine. It starts it, calls it. Then when a coroutine stops, it raises stop iteration, and the return value from the coroutine is stored in stop iteration.value. And this is a very important part. Here, we're essentially checking that the coroutine that we started didn't suspend. So normally, what a coroutine is, a definition of coroutine is a function that can suspend multiple times. So there are multiple entry points and exits from that function, and the event loop is essentially looping through invocations of that coroutine until it fully executes. Well, in our case, our rudimentary event loop cannot handle any of that. It expects that coroutine to complete fully in just one iteration. So we start it, and it must go to completion. So from start to return. And this runtime error essentially is an invariant that enforces that. All right, so let's recall how that network driver might be constructed. We have a chain of calls, a chain of availabilities like this. And somewhere deep in that chain, we have a call to a socket, or a stream, an async IO stream that tries to read those bytes from the network. And this is where normally in your async IO program, you would suspend that coroutine execution. Because there are no bytes in the network yet, you're waiting for those bytes, you're giving the opportunity for some other network operation to complete, some other task to complete. Well, in our world, we're essentially writing async drivers, which blocks, right? So there is no concurrency whatsoever. Okay, cool. So what can we do? This is how basically that async protocol looks, right? It could be an async IO transport, async IO protocol, or it could be a stream interface like this. In our sync version, what we do is we take that, throw away that stream, and replace it with a blocking socket. This is all we need to do. There is no more yielding, right? So this way, we ensure that all that stack of coroutines never yields. And boom, this is all we need to do in order to turn our fully asynchronous client into a synchronous client without any code duplication. So you only need to replicate a little bit of that facade. All right, so what are the caveats here? Since all those functions are still async, we didn't physically remove the async definition. It's somewhat more expensive to invoke them because of how Python sets up the code object and the coroutine object, but it's marginal. Naturally, we don't have any event loop. It's just our call coroutine hack. So if your code relies on async IO create task, futures, callbacks, timeouts, any of that stuff, that wouldn't work because there is no event loop to enforce that. But usually, if you're just writing a network client, that network client is usually just a really simple stack, call stack to a network socket with some usually synchronous logic that processes data from that socket. All right, so that was the first hack. And now let's talk about a topic that is dear to my heart as a database developer, and that's transactions. So many of you probably heard about the term ACID, which stands for atomicity, consistency, isolation, durability, which is a set of properties that describe a well-behaved database system, right? And all of those we can be talked at length about, but today I would like to focus on atomicity. Atomicity essentially means that a set of instructions that mutate some state are treated as a whole. So if you have 5 statements that modify some data, either all of them succeed or the entire operation essentially is rolled back. None of them have any effect. This way, you can retry your operation or just generally enforce that there is no intermediate broken state in your data. All right, so normally this is something that your database would do for you, right? But there are sometimes some cases where transaction atomicity is a kind of a cool thing to have in your program when you have a piece of data in memory that you want to modify in a way that is atomic. So let's look at an example. This is a table, essentially a table of accounts representing users and the amount of credits they have, or dollars, or whatever the denomination is. And let's pretend that we're building a system in which users can essentially settle accounts between them, settle expenses. Like they're going out, the 3 of them, and then say Carol picks up a check at the end of the dinner, and then they need to split that somehow. All right. So let's see. A very trivial implementation of that is basically 2 functions. We withdraw and we deposit. And this way we subtract the amount from one account and add it to another account. And of course, we have a check there that prevents us from from going into negative. All right. So now we have our function that settles that shared expense equally between accounts. We withdraw half from Alice's account, half from Bob's account, and deposit that amount to Carol's account. All right, so let's see. Let's say the expense was 20 credits. Well, whoops. It turns out that Bob is poor, doesn't have any money, and so this transaction fails, saying that Bob has insufficient funds on his account. All right, cool. So let's try and handle that error, and let's inspect what happened to our accounts dictionary. Well, oops. Turns out that we have withdrawn from Alice's account because she had enough, and because the whole operation now aborted, we ended up with less credits in Alice's account than there was in the beginning, but that amount never went anywhere. So we have an inconsistent state. So it's not atomic. All right, so how can we fix this? The simplest, easiest way to do this is to take the snapshot of your state before you mutate it. So in case if it fails, then you can roll back to that earlier snapshot of yours and just throw away all the mutations that happened midway through. So we have a dictionary, and we make a copy of that dictionary. And since we're returning copies now, our settle shared expense function can be written as this. So this is all cool. We repeat the same thing. And now if we print the accounts now, we see that the amount is correct. So we rolled back our transaction and nothing happened. It's all cool. We have no inconsistency in our system. So we achieved that atomicity. Well, awesome. We fixed our problem. Now, what is the issue with this solution? Well, it turns out that if you're making tons and tons of copies of your data, if that dictionary is very large and you're doing a lot of these operations, you will see that even though dig.copy is really, really super fast, once you start going to like approximately 10,000 elements in that dictionary, it's becoming non-negligible, right? So you're looking at almost a millisecond of CPU time just to do that copy. And a millisecond is an impossibly long time for a computer, because Postgres, for example, can run an amazingly complex query in that amount of time. All right, so what can we do? we can pick a better data structure than a dict. So what is it? HMT is a hash array map trie. It's a very interesting data structure that is used in many functional languages mostly to implement mappings. It's a persistent mapping. And what persistent means is that whenever you mutate that map, you always get a reference to the previous version of that map. So it's structural sharing. So here's how the API for that looks. It's very similar to tuples, right? We mutate the map and we get a copy of it, a reference to a copy, and we still get the reference to the original. So normally dicts are implemented like this. It's a hash table where we have hashes of elements pointing to values. A hash trie, on the other hand, is a tree. It's a sort of a tree where those hashes are, those subtrees of that tree are effectively shared. So if you mutate just one branch of that tree, all the other data is going to be shared. There is no copying. That's how you can achieve really, really efficient mutation without overhead. All right, so let's see how that API can look now. So you notice that not only our code got shorter, basically, in the process. So let's see how that looks in terms of performance. This is not an entirely scientific chart, but if you can see the red line down there is persistent map. So this is essentially a difference between ON versus O log n in terms of complexity. So this hack is basically when you need to copy, to ensure atomicity of some data in memory, reach out for immutables. They're great. All right, and the last thing I would like to talk about, we have a few minutes left, is something that I think is pretty cool, and that's dispatch. So frequently, we have situations in code that we have ladders and ladders of is-instance calls like this. Well, we don't have to use that. Use single dispatch instead. It's great. It's been in Python since forever. And especially if you use type annotations, it's even nicer. But you don't have to stop at dispatching on types. You can dispatch on values as well. And this is a common pattern where, for example, you need to handle some sort of error, you need to dispatch on its code. Well, the same pattern applies. It doesn't have to be a type, because a type is just a value, and you can dispatch on any value. And this results in code that is easier to maintain and essentially just being nicer to read and write. It's not part of the standard library, but we have a reference implementation for it in the EdgeDB repository, so if you're interested to take a look or just copy it, feel free. All right, and that's it. Thank you very much. Those were the 3 hacks. Questions?
Thanks very much for your talk. Returning to your first instance of turning async code into sync code, I wonder, your solution was extremely elegant. On the code generation side, I wonder if you considered manipulating the AST of the sync function, of the async function instead. It would be more reliable and it would address some of your caveats.
To be clear, we haven't even tried to do the code mode route because we knew that it would essentially still be a lot of work that you need to do, and the downsides still apply. You still have that compilation pass. You still have to inject it into your flows, basically. You no longer have this nice pure Python code base that you hack on normally, but just modifying it and running it, right? But yeah, of course, if you want to implement code modding, and certainly that solution, that hack, wouldn't be useful for everybody, because some code bases have maybe slightly more complicated code, maybe more transformation is needed. And yeah, by all means, then AST code modding is obviously a lot more reliable, for sure.
Thanks.
So the async sync thing is something that obviously a lot of libraries have to deal with, and I'm wondering, has the wider ecosystem caught on to your technique there at all? Is that something that other people would adopt as a way of accommodating both modes of programming?
It's a very good question. I don't believe so. I could be wrong, because this is sort of a thing that a lot of people probably stumbled upon. There was this very, very long discussion thread in the URL lib3 repository where they've basically been discussing exactly this issue. Right? So URL lib3 is a synchronous library, but wouldn't it be nice to have an async version of that? To my knowledge, I don't think any, at least popular library uses this approach. Perhaps we need to work better on popularizing it. And I think maybe, so it's actually being used successfully by us for the EdgeDB database driver, which is really similar to Postgres in terms of its protocol. So I think what we can do is apply this to async PG to have a synchronous version of that, and that way expose more people to this approach.